Assalamualaikum and very good day to everyone. We are from Group 8. Today we will present two applications of ODE in chemical engineering industry. Firstly, we will discuss about Newton's law of cooling, which have first order of linear non-homogeneous equation. Secondly, we will also discuss about fluid dynamics and process safety, which have first order of non-linear homogeneous equation. So for the context 1, in a batch of chemical process, an exothermic reaction generates a massive amount of heat. To prevent a thermal runaway explosion, chemical process safety engineers design cooling jackets around the reactor vessel. Cool waters flows through this jacket to continuously remove heat. For problem statement 1, a batch reactor contains 1000 kg of a liquid reaction mixture with a specific heat capacity that equal 4 kJ per kilogram degree Celsius. The reaction is completed and the mixture is initially at a dangerously high temperature, which is at 0 seconds, and the temperature is 150 degrees Celsius. To cool it down, water at a constant temperature of which is 20 degrees Celsius is pumped through the cooling jacket. The overall heat transfer coefficient multiplied by the area is equal to 8 kilowatt per degree Celsius. Assuming no further heat is generated, Newton's law of cooling models the systems. Find the temperature profile of the mixture over time in seconds and calculate how long it takes to cool the reactor to safe, which is 40 degrees Celsius.
So we go to the first solution. We use the Newton law of cooling and formula of heat energy. We apply Newton's law of cooling by setting the rate of heat loss equal to the rate of energy change, and we derive it and we get the equation mc dt over dt equal to negative ua multiplied by t minus tj. And next we substitute the information given and we get dt over t minus 20 equal to negative 0.002 dt. Next, we separate the variable to get all the temperature terms on the left and time on the right. Integrate both sides and solve the t, giving us the general solution. For the next slide, we solve for our integration constant C1 using the initial condition that the temperature is 150 degrees Celsius at time 0. We get C1 equal to 130. This gives us our specification for this system, and we need to find how long it takes to cool down to 40 degrees Celsius. We substitute the temperature into the equation and our final time is 935.9 seconds.
For context 2, chemical engineering faculty design drain edge system for steel storage vessel. Understanding how fast a tank drain is critical for process scheduling and emergency safety procedure, such as quickly emptying a vessel containing a runaway reaction. Because the cross-sectional area of the conical tanks changes with depth, the rate at which the liquid level drop is non-linear. For problem statement 2, conical storage tank filled with a liquid chemical is shaped like an inverted cone with a top radius is 3 meter and a total height is 9 meter. Liquid drain out of a small hole at very bottom vertex of the tank. The area of the drain hole is 0.01 meter square. According to Torricelli's law, the velocity of the exciting fluid is square root 2 gh, where the g is 10 meter per second square, is the acceleration due to gravity, and h is the instantaneous height of the fluid. If the tank is initially completely full, h equal to 0, is equal to 9 meter. Derive the differential equation for the fluid height, ht, and calculate how long it takes for the tank to empty completely.
So for solution 2, we are given the information, and we know that the flow rate out is equal to n0 square root 2 gh, and we can make a ratio of r over h equals to 3 over 9. So we can make a new equation which is r equals to 1 over 3h. For cross-sectional area, we got the equation of a h equals to pi r squared. So we substitute r from the new equation that we just derived. So we got a h equals to pi over 9 h squared. And we know that dv over dt is equal to negative flow rate out. So for v is equal to integrate a h dh. So we got dv over dt is equal to ah dh over dt, and we got ah dh over dt is equal to negative a naught square root 2 gh. So we substitute the value and then we got pi over 9 h squared dh over dt is equal to negative 0.04472 square root h. And for the next slide, we integrate both sides so that we can get the new equation 2 over 5h to the power of 5 over 2 equals to negative 0.12812 plus c. And then we substitute t equals to 0 and h at time equals to 0 is 9 meter to get the value of c. And then after that, we just substitute back the value of c so that we can get the value of time is equal to 758.66 seconds.
For reflection, this project served as a profound exercise in critical thinking, technological adaptability, and lifelong learning. By developing and solving these two distinct ODE models, we moved past static equation to master transient real-world behavior. Critical thinking helped us bridge heat transfer and fluid dynamic under a single mathematical